Good morning to everyone. We are from Section 1, Group 10. The title for our group project is Flash Calculation to Separate the Mixture between Acetone and Methanol. Our team members have Tan Yipong, Chua Sherwin, and me, Li Wanning. Let's start by looking at the introduction to flash distillation. The working principle of the flash distillation works by heating a liquid mixture and then rapidly reducing its pressure to separate into vapor and the liquid phases based on the different volatilities of its component. The advantage is separating pure components from multi-component systems, and the process is easy to understand and low cost, while the disadvantage is similar volatility cannot be separated and not efficient for binary system. The application for the flash distillation is often used in the petroleum industry. This is a simple diagram of the flash distillation. Before the liquid mixture enters the flash distillation, it is heated at the tubular heat exchangers, that's shown in the diagram. The hot liquid mixture is then fed to the pressure-reducing valve to a separator where the pressure is reduced adiabatically to produce vapor at the expenses of the liquid. The liquid is withdrawn from the bottom of the separator while the vapor is accessed at the top of the separator and it is condensed in the condenser. Before we do the flash calculation, we need to determine the process and composition condition, which is overall composition, operating pressure, and the operating temperature. Our basis is 100 mol per hour of reaction mixture. The composition of the acetone is 0.6 mol per mol, which is the component 1, while the component 2, methanol, is 0.4 mol per mol. The operating temperature is 60 degrees Celsius, while the pressure is 101 kPa. There are a few of assumptions we are made, which is the reaction mixture are ideal gas for the vapor phase, and ideal solution for the liquid phase, which is the simplest form of Raoult's law, can be used.
For the calculation part, firstly we have to find the P saturated for each components, and in order to find it we can use the Antor equations by referring to the table B2, and we found that for the acetones is around 115 kPa and the methanol is 83 kPa. And next we have to find the bubble pressures, which we can use the equations. Bubble pressures equals to summations of the Zi's multiplied with the Pi sets. By substituting all the values, we are able to find the bubble pressures is around 102.6891 kPa, and we also have to find the due pressures, which using the equations 1 over the summations of molar compositions over the P sets, and substitute all the value. We found that the due pressure is around 100 kPa. Next is using the definitions of Raoult's law to find the Ki. The Ki is equals to Yi over Xi, also equals to the Pi sets over the total pressures, and K1 is around 1.1402 kPa and the K2s is 0.8316 kPa. And to find the molar fractions in the liquid phase, the molar compositions in the liquid phase, we can use this formula, which is the Xi equals to the P minus P2 sets over the P1 sets minus P2 sets. Substitute all the value for the X1 is 0.545x, and to find the X2 we can just use the 1 minus X1, and the result is 0.4542. And next is to find the molar composition in the gas phase. We can use the previous formula, which is the Yi equals to the Ki multiplied with the Xi, and we found that X1 is equals to 0.6223 and the Y2 is 0.3777. And next is find the V initials. In order to find it, we can use the equations of the 13.107, which we arrange it and it will become this form, and we substitute all the values and we found that the V initials is 0.7084. And lastly is using the iteration methods to find the V molar fractions using this formula, and by substitute all the values and we iterate it, we found that the V is 0.6975 moles, and to find the L we can just 1 minus V, and we found that the molar fractions of liquids is 0.3025 moles.
So now let's proceed to PXY diagram of the process. So in this graph, the red line represents the liquid line and the blue line represents the vapor line. And this graph is at constant temperature of 50 degrees Celsius. So we can see that the initial composition of acetone that entered the flash column is 0.6 at the pressure of 70 kilopascal. So by plotting on a point based on these two conditions, so we can see that it is located at the equilibrium region. So when we connect the point to vapor and liquid lights so that we can get the vapor composition Y1 and also the liquid composition X1 from the graph. And the value get from the graph is approximately what we get from the calculation by using the formulas. So the next diagram is T versus XY diagram at constant pressure of 70 kilopascal. So we can use the vapor liquid equivalent graph to identify the vapor and also the liquid composition, which are the X1 and also the Y1 at the outlet of the flash column. So by plotting the point at 50 degrees Celsius and also 0.6 composition, so we can find that the acetone is in equilibrium in this condition, and by extending the line to vapor and also the liquid line, we can also get the X1 and also the Y1. So lastly will be our process flow diagram. So we assume the flow rate of the feed stream is about 100 mol per hour, and it contains acetone methanol mixture at 60 degrees Celsius and also 101 kilopascal. So at the product stream of the flash column, it will produce vapor and also the liquid phase of acetone and methanol. So in the vapor stream, it consists of 0.6223 mol of acetone and also 0.3777 mol of benzene. And in the liquid stream, it will consist of 0.5458 mol acetone and also 0.4542 mol benzene. So as we can see that the both stream is rich of acetone, so because of the boiling point and also the vapor pressure of these two substances is really close, and so it will reduce the effectiveness to separate these two substances.